You know, in the world of science, we're always searching for new materials to build the future. But what if the next game changer isn't a material that's a specialist at just one thing, but one that has a whole bunch of hidden talents? Well, today, we're diving deep into a fascinating compound called lanthanum platinum germanium. Let's find out what makes this thing so incredibly special.
Okay, so to really get why this one material is such a big deal, we've got to zoom out and look at the big picture. It all starts with the global push for renewable energy, right? That leads us straight to a really cool class of materials called thermoelectrics. And inside that group, there's a family called skutterudites that are just packed with potential. And that brings us right here, to our case study, LaPt4Ge12, a material that perfectly shows off what this whole field is about.
So yeah, that's what this is all about, the hunt for supermaterials. As our technology gets more and more demanding, we need stuff that can do more than one thing at a time. We need materials that are truly multifunctional.
And at the absolute core of this whole story are thermoelectric materials. Just think about it for a second. All the waste heat pouring out of our cars, our factories, even our computers. What if you could just capture that heat and turn it straight into electricity? No moving parts, no noise, no pollution. That's what thermoelectrics do. It's an unbelievably elegant way to make power out of something we'd normally just let disappear into the air.
Okay, with that in mind, let's zoom right in on our star player today, LaPt4Ge12. I mean, sure, it's a combination of a few elements on the periodic table, but its real magic, its secret sauce, is all hidden away in its unique atomic structure.
And here it is. This gives us an amazing peek at what's going on inside. It forms this really beautiful, complex, almost cage-like structure. See, the lanthanum atoms are basically trapped inside these little cages made of platinum and germanium. Now, those trapped atoms can rattle around like a pinball, and that's fantastic for scattering heat. It keeps the material from getting too hot on one side. But at the same time, the cage itself is like a perfect superhighway for electricity to flow through. And that's the magic recipe for a great thermoelectric. It blocks heat, but lets electricity pass.
And this amazing structure isn't just a one-off. Our material belongs to a whole family called skutterudites, and they're all known for this special cage-like setup that makes them so incredibly promising for turning waste heat into useful power.
So we know it's a solid candidate for thermoelectricity, but honestly, that's just the beginning of the story. Let's start unpacking the other key talents that researchers have found, the ones that make this material a true Swiss Army knife. This here is basically our roadmap. We're going to look at this material from 4 different angles. First, how tough it is, its structural properties. Then, how it behaves under different conditions, its thermodynamics. After that, we'll get into its really surprising magnetic side. And finally, we'll see how it performs not just with heat, but with light too. Let's kick things off with its first talent. Because look, before any material can be useful, it's got to be able to handle the real world. And this stuff, it's exactly that, strong and stable. But how strong are we talking? Well, scientists put a number on it, a bulk modulus of 116 gigapascals. Now, in plain English, that's just a fancy way of saying it really doesn't like to be squished. It tells us the material is mechanically tough and can handle a whole lot of pressure without breaking a sweat.
And it's not just tough on its own. When you put it side by side with its chemical cousins in the skutterudite family, you can see it holds its own perfectly. It's right in line with its relatives, which confirms it's a seriously robust material. The data also hints that it's got a great mix of strength and flexibility, so it's not super brittle either.
Okay, let's move on to its second talent, and this is probably its most famous one. We're talking about its amazing ability to efficiently turn heat into electricity. This chart right here shows us something really cool about the material's efficiency. Scientists call it the figure of merit, or ZT. You can think of it like a report card for how good it is at its job. And you can see a clear trend. As the temperature shoots up, its performance gets better and better. This material absolutely loves the heat.
Its peak efficiency hits ZT value of about 0.26 at a scorching 1000 Kelvin. That's over 1300 degrees Fahrenheit. And what that means is that this material does its best work under the exact high temperature conditions you'd find in places like industrial exhaust pipes. That makes it a perfect fit for capturing all that waste heat.
All right, now for talent number 3, and this is where things get really unexpected. Beyond being strong and great with heat, this material also has a secret magnetic side. This brilliantly shows us where that magnetism comes from. It's actually a really subtle quantum effect. So the green line shows how the material's electrons are normally arranged. But because there are heavy atoms inside, you get this effect called spin-orbit coupling.
And when you account for that, as you see in the purple line, it causes a tiny little split in the energy levels. It's that split, that tiny little difference, that actually gives rise to magnetism. It's wild.
So what you end up with is a small but definitely significant magnetic moment. Now, it's not going to stick to your refrigerator, but this weak magnetism is incredibly exciting for a whole new field called spintronics. That's a type of technology that wants to use an electron's magnetic spin, not just its charge, to store and process information. We're talking about the potential for way faster and more efficient electronics down the road.
And that brings us to the final talent on our list today. As if this material didn't already do enough, it turns out it's also excellent with light.
To put it simply, it's very shiny. The research shows it has a high reflectivity of about 0.83. That means it bounces back 83% of the light that hits it. This opens up a completely different set of possible uses in things like optical coatings, high-tech sensors, and other devices that need to control light with precision.
So let's just recap for a second. It's strong. It turns heat into power. It's magnetic, and it's great with light. This brings us to the real takeaway here. The future is multifunctional. Having all of these different abilities packed into a single material is a massive deal.
This quote from the research paper just says it all, perfectly. It's not about any single property. It's about the synergy between them. The way its toughness, its ability to conduct electricity, and its linked optical and magnetic properties all work together. That combination is exactly what scientists are looking for to build the next generation of devices.
And because it has this incredible combination of traits, it's a potential candidate for a huge range of things. Its heat-to-power skill is perfect for energy converters and waste heat recovery. Its talents with light point toward advanced photonics, and that unique magnetic thermoelectric link could help create entirely new fields, like spintronic thermoelectrics.
The story of LaPt4Ge12 really shows us that the future of materials science is all about finding these incredible materials that can do it all. And it leaves us with a really exciting question to chew on. As we discover more materials like this, what happens when one material can do everything?